very happy to see so many people here this early in the morning. Today we're going to understand some real clever and smart techniques on building declarative algorithms. This continues what we did on laziness and what we did on single assignment. So this continues, and it's kind of very smart and clever use of lazy evaluation and of single assignment. I'm going to be showing lots of code. So the motivation is we want to write efficient algorithms that are still declarative. You know, the main theme of the course, or one of the main themes, is that you really want to write your programs declaratively. It gives you so many advantages, and it's more and more going on, and I'm sure in 20 years it'll be even more like that. And that's what I'm going to talk about today. We're going to use some concepts. I'm going to talk about algorithms. So first of all, single assignment and lazy, we saw it, but I'm going to talk about amortized and worst case performance for algorithms. I'm also going to talk about something new. Amortized you maybe have heard, but I'll talk about something you probably haven't heard, which is an ephemeral and a persistent algorithm. It's a kind of very interesting and very powerful idea. And we're going to give a bunch of algorithms today. And then I'll show you one concept called a difference list. This lets you do append of two lists in constant time operation, and it's declarative. And then I'll show you a bunch of data structures, actually a queue, but with different techniques. So we're going to always use the same queue with the same interface, but they will get smarter and smarter as the course goes on, okay? I'll start with a naive queue. If you're really naive, you do like that. But then we make it smarter. I make it amortized constant time, worst case constant time, and then I will make it persistent, okay? And I'll explain to you what it means. And that makes the algorithm actually very, very powerful. So you'll see that in the course. Okay, so just a little motivation. So we want to write code declaratively because that gives you huge advantages for testing, for concurrency, for distribution. It really makes life easy. So we want to stay there as much as we can. And today I want to talk about algorithms, not just programs, but specific algorithms doing some specific task, like a data abstraction. And that algorithms manipulate data structures, and sometimes they need mutable state. You write them in Java, you will be doing updates of variables. And the question is, do you really need that? Okay. Can you make the algorithms efficient in just purely declarative? And sometimes you can, and sometimes you can't, but many times you can, okay? They can often be efficient, and today I'm going to show you some clever techniques on how to do that, okay? Some of these techniques come from a very good book on how to build declarative algorithms called Purely Functional Data Structures by Chris Okazaki. So here's the book. And this book has many more examples that I'm going to show you. And it really shows you how to make declarative algorithms efficient. Okay? So this is a good book. Maybe I can pass it around. If you want, you can look at it. This book uses different notation. It has many examples. You can just take a look. It uses another language called standard ML, which is a functional language with explicit lazy evaluation. So that's not so hard to translate into us, okay? So we're going to use some of the examples I'm going to show you are taken from this book, okay? Okay, before I show you lots of code, I want to present the concept. So we're going to have algorithms today. So we're going to talk about algorithm concepts, okay? And there's the following. There's three kinds. First of all, language. We're going to use declarative paradigms, powerful ones, and the concepts we use are going to be the single assignment variables, which I call data flow variables, also lazy evaluation. So that, we saw that already. This is what we saw. But there's new concepts for today. First of all, in complexity. So you've seen already, I'm sure, in other courses, complexity of algorithms, time complexity. Here we're going to focus on upper bound and two kinds, amortized and worst case complexity. Amortized is kind of something you can sometimes get. It's easier than worst case, but it's not as good. So I'll explain that. And the final one is ephemeral versus persistent. Now, this is something you almost surely, I don't think you've seen it. So far in your life, you've always worked on ephemeral data structure. So I'll explain what it means and why, what is this new thing, persistence, and why is it nice, okay? So first, amortized. Amortized complexity means if you do lots of operations, maybe most of them are cheap, but one of them is expensive. Well, that's not so nice. So the worst case is very bad. But still, on average, it's good, okay? And so if you have n operations, combined, they have a complexity of f of n, but then each single operation you divide by n. So there's like an average per operation, which is fn divided by n. Individual operations can be mostly cheap, and sometimes expensive. So if I have a queue, for example, so I start here, and I do an insert, and then I do more operations. So I'll make a diagram here. And each time I do an operation, insert or delete, I will get a new queue. And maybe the time of most of these is 1, okay? But then there's one operation here which has time of n. Well, if I have n operations that have time 1 and one operation of time n, then the user, on average, will still see constant time, okay? Because the n here is like spread over all the n sequence. And that's usually good enough, very often. For human beings, you're doing stuff, most of the time it's fast. Sometimes there's a slow thing in there, but that's sometimes okay. If it's, on average, very, very fast. Okay? So this is the idea of amortized complexity. Okay? And then there's the other idea, which you saw before, which is worst case. This is the standard big O. So the worst case means you're looking at the single operation. Here, the worst case complexity is n. The worst case is n, but the amortized is 1. Okay? Now, what you really want is the worst case to be 1. Okay? You don't want the n here, but maybe you can't get rid of it. So this one actually has a very bad worst case, but much better amortized. Okay? So amortized is something that's like a compromise, okay? Sometimes it's good enough. And I'm going to show you some amortized algorithms today. You see how it works? The other notion is ephemeral and persistent. So ephemeral, the word ephemeral means something that is very short-lived. It's very transient. It only exists for a short time. A fly will only live for 1 day. It's a very ephemeral creature, okay? And for a data structure, an ephemeral data structure, it means you have only one version at a time. So what does that mean? If I have a queue, Q1, and I do Q2 equal insert Q1 of A, I create a new queue, Q2. Okay, that's reasonable, huh? But Q1 is not valid anymore, in fact. I destroyed Q1 to make Q2. So the Q is ephemeral. There's only one version at a time. Okay? When you build data structures stateful with variables that you can update, they're always ephemeral. When you change the attributes of an object, the old attributes, the old values are gone, of course. Huh? They're forgotten. So the old value, the old version is gone. That seems to be very obvious, huh? It's gone. So you only have one version at a time. So an ephemeral has only one version at a time. So I can make a picture again. So here, for example, I have Q1. I do an operation. I get another Q2. But once I create Q2, Q1 does not exist anymore. Q3. Once I create Q3, there's no Q2, and so on. Huh? So there's only one version at a time. But there's actually another kind of data structure. And this one is called persistent. And this one you can have many versions at the same time. So if you're given a Q1, you do Q2 insert just like before. You have a new Q2. Huh? But Q1 is still there. It's still usable. So Q1 does not go away. And if you do Q3, you can do Q3 is insert Q1, and that one will work too. Okay? So you can have many, many versions. So the way it works is if I have Q1 and I do an insert, I have Q2, but the Q1 is still existing. So if I do another insert from Q1, it works. And now I have two versions. And I can keep going, and I can create many versions. Each time I will create many versions. Of course, you might say, well, this is going to use up lots of memory, right? Well, actually, if these data, the old ones are not accessed, then the garbage collector will remove any of the data. So this actually works fine. Okay? So why is that useful? Okay, this is the persistent, and this one is ephemeral. So why is persistent data structures, why is that useful thing to have many versions? Actually, it's really, really useful, okay? And you already are using it, actually. It's used for, typically for collaborative work. Let's say if you have two people editing the text, and they make their own versions, local versions. That's an example of a persistent data structure. The single version becomes two versions, okay? And also, a repository like GitHub, software repository, they allow having many versions of software. So this is actually a very common thing. Yeah? You can also have databases with multiple versions. If you need multiple ways of using the data, then you can have different versions, and they can exist at the same time. You might have a recent version or an older version, and they both exist. Okay. So that's actually it's very useful. And if you can do it cheaply, it's actually very nice to have. It's also useful if you want to do like an undo very cheap. You can always go back to the old version. Okay. It's very easy. It's just sitting there. And you can even use it at the same time as the new one. Okay. In systems that have mutable state, like Java, you can get kind of mutable versions by doing copy. You make a copy, okay, of some data structure, but there it's the programmer that has to handle it. It's very clumsy. The copy is a new thing, and you have to be careful about the original and the copy and so on. So in the code I'm going to show you today, it's all automatic. You use the data structure, and the old versions, they still exist, and you can use them, okay? There's no, you don't have to do it, the programmer doesn't have to do anything special. Okay? And a final point, if you have multiple versions, it's often a good idea to have a way of combining versions. Maybe we want to combine Q2 and Q3. Maybe two people work on a text separately, and then somehow you want to merge. They do local work and you merge. And so a merge is actually a useful kind of operation for persistent data structure. So I'm not going to talk about merge today, but it's easy to add the merge for if you need a data structure. that can do that. And the merge, sometimes it's tricky because you might have conflicts. If you have, in GitHub, it has a special way of handling that. So any place where there's a potential conflict, it will tell you, okay? But often other data structures, you can just do merge. If you have sets, for example, you can just do the union, okay? So that's what we're going to talk about. Ephemeral, persistent, and worst case amortized. And I'm going to show you a lot of code for that. Okay, so let me give like summary of what we're going to see today, or today and next week. I'm going to show you 5 ways to do a cube. And it'll always be the same cube with the same interface. But the algorithm will have different implementation, different complexity, okay? And they're going to use different paradigms. So these different algorithms, some of them will have different paradigms. And I'm going to show you 5 here. The blue one here is the naive cube. It's really the worst of all, okay? The insert is constant, but the delete is order n. Delete is slow. But you'll see when I show you the code, but it's written in functional programming, sequential functional programming. I can make it a little bit smarter. I can make it amortized constant time, where the insert and delete are both constant, but amortized. That means maybe the delete is still expensive, but it's rare, okay? So it's kind of better, amortized constant time. But what I really want is worst case constant time. And in order to do that, I need to use single assignment variables. If I do that, I can show you a worst case constant time. Insert and delete are constant. But both of these are ephemeral, okay? That means once you do something with a version, the old one doesn't exist anymore, okay, or it's not usable. And if you want persistent, then you can use lazy evaluation. This is another very interesting use of lazy evaluation. It makes it possible to get persistent algorithms. So that's pretty amazing, okay? So this is another of the powers of laziness, that with laziness you can build persistent algorithms. And I'm going to show you an amortized constant time persistent cube, and then a worst case one. This one is actually, you have to be very careful in how you organize the lazy stuff, okay? So laziness will give you persistence, which is very nice, actually. So here's kind of a graph of what we're gonna, the things. So we have this queue here. It can either be ephemeral or persistent. The ephemeral one, we have the amortized in the worst case constant time, and persistent also, amortized worst case, okay? And so I'm going to show you the code for all of those and explain it. The amortized ephemeral is the easiest. If I add single assignment variables, like the data flow variables, I can get a worst case ephemeral, which is good. And if I want to make it persistent, I will be using lazy evaluation. Okay? So this is a good diagram to keep in your head. So you can see how the more powerful paradigms let you do better, smarter algorithms. Okay? So that's how we're kind of going to organize things. Okay. So in order to warm up a bit, I'm going to show you a data structure which is actually a list called the difference list. So this is actually very similar to the worst case ephemeral cube. It's kind of the same idea, but this is a really powerful declarative data structure. So I want to show it to you. This lets you make list append in constant time, okay? Which is very nice, huh? If you can do it. So a difference list is a representation of a list. I'm representing a list as a pair of two lists, okay? So I'm going to show you examples of this. So what does that let you do? So if I have a list, some list L, I will represent it as two lists, S and E. So this is a representation of a list. It's still just a list, but I'm representing it in a funny way as two lists. Okay? And E is the suffix of S. So for example, if the list L is 1, 2, 3, 0, then SE could be 1, 2, 3, 4, 0, followed by 4, 0. Okay, two lists. And the list that I represent is the difference of those two. This 1, 2, 3, 4 minus this one. So this one has to be the suffix. It has to be at the end of the other one. So E is a suffix of L. So the difference is SE represents the list S minus E. We take S and remove the suffix E. Okay, so that seems fairly straightforward, right? Now, it gets really nice when you start using unbound variables. What if I do this? Where X is an unbound variable. This one, it will be bound to a list, but I don't know which one. So I just put an unbound variable here. So 1, 2, 3, X and X. Well, this is also the same thing. This is also the list 1, 2, 3. You see, so this is a flexibility you get when you use unbound variables. So the list 1, 2, 3, 0, there's many ways to represent it. 1, 2, 3, X, comma X. 1, 2, 3, 4, Y, comma 4, Y. Or 1, 2, 3, 4, 5, 0, comma 4, 5, 0. There's many ways to represent it. Okay? So you say, okay, so that's kind of funny, right? I represent the list 1, 2, 3, 0 in different ways. Okay. Well, what does it get me? What can I do when I have that? When you have that, you will see you can really do interesting things. First of all, you can add elements to the back and the front in constant time. You can start manipulating this thing. So given a difference list, SE, and assume that E is an unbound variable, okay? It's like kind of like this, 1, 2, 3, X, X. Okay? Now, how do I add, let's say I want to add a number to the beginning of this. I want to add 4 to the beginning of this. Well, that's easy, I just add 4 to this one. So I get 4, 1, 2, 3, X, X. So if I add 4 to the beginning, I can do it by just adding 4 to the first one. But how can I add 4 to the end? So what I want is something like 1, 2, 3, 4, Y, comma Y. Okay? So if I want to add 4 to the end, well, I will bind X. If I want to add 4 to the end, here I'm adding it to the beginning, to the start. If I want to add 4 to X, I bind X to 4Y, and then I use the first argument, which is 1, 2, 3, 4Y, and I replace the X by Y here. I use Y. And now I have 4 at the end. 1, 2, 3, 4, Y, comma Y. So this is the list 1, 2, 3, 4. Okay? This is constant time operation. Okay? It's only one binding. I can add an element to the end in one binding, and it's still declarative. That's kind of neat. And if you have a regular list like 1, 2, 3, 0, you can't do that. What if I want to add 4 at the end here? Well, this is like a value. You cannot modify it. you have to traverse the whole list and make a new list with 4 at the end. So it's order n. If the list has a length of n, adding an element to the end takes order n usually. But for the difference list, it's constant time. See, that's nice, huh? And it's still declarative because we're using the unknown variables here. So adding an element can be either done at the front or the end in constant time. Note, you can only do it once, huh? Once I bind x, it's done. I cannot bind it twice. I can only do it once. So the limit here is that I can add an element to the end in constant time, but only once. And that's it. I have a one-shot thing, okay? But the advantage is it's still declarative, okay? And you can do even more than that. You can actually do appending two lists in constant time too. So how does that work? So if you have two difference lists, so here's S1, E1, that's one, and another one, S2, E2. Assume the E here is an unbound variable. You can assume that. So we're like here, we're not there, but we're here. If I have those two, the way to append them is to bind E1 to S2, and then I take S1 and E2. Okay? So if I have, for example, A, B, X, that's one difference list. This represents the list A, B. And I have another one, which is 1, 2, Y, Y. This represents the list 1, 2. If I want to append them, I will bind the X to 1, 2, Y, and then I will take the two exterior guys, the first one here and the last one here. So if I bind X to 1, 2, Y, then I will get A, B, 1, 2, Y, and here I'm using Y. You see, I've actually appended, because the X is also here, I've actually appended 1, 2, A, B, 1, 2, and the result is a new difference list. So you see, I'm actually doing an append. And again, this is constant time. So a constant time append in a declarative language. So this is a neat, a very nice representation of the difference list. Of course, it's again a limitation. You can only do it once. It's ephemeral. Okay? That means once you bind the X here, once, you can't bind it a second time. Okay? It's over. But that's usually good enough. When you build a big list, let's say I'm building a list by bringing lots of small lists together. That's very common. Then it's okay. So in most cases, it's fine. This is actually handling most of the use of append. Okay? So remember, I used append in the quicksort before. Actually, you can rewrite quicksort to use difference lists, and it does not need append. Okay? I used append because I wanted to show a simple algorithm. I didn't want to bring in new complex things. But every time you use append to build a list, you can ask yourself, aha, can I use a difference list here? Okay, and usually it's possible. And in Quicksort, you could rewrite it to use difference lists. Okay. Okay, I'm going to give you now an example of that. I'm going to show you a program that does some computation on a list, but then we're going to use difference lists. Okay. So here's a function that maybe you have seen before called flatten. Flatten takes a list, but the list can have lists and so on. Lists with lists with lists, okay? And all the lists are removed, all the elements are brought together into one big list. So something like flatten with list 1, 2, 3, 4, 5, it gives you flatten 1, 2, gives 1, 2, 3, 4, 5. So flatten, if you have like a list of lists, it flattens it so you only have one list. And this uses append. So here's append. I just wanted to show it to you. Okay. This is append. Here you have a case. If x, xr, if x is a list, so x, xr, and then is list x. If x is a list, then I will call flatten on x and on xr. You see, then if x is a list, I do a recursive call, flatten, but that gives me a list. So here I have two lists, and so I append them, okay, like that. And if x is not a list, I just add it as an element, x bar flatten, okay? And if xs is nil, it's nil. So this is the flatten definition. Works fine, except it's kind of too expensive. I'm doing all these append operations. The more I have nested lists, the more I'm going to be doing append operations, okay? When I flatten x, I have some list here, and the time of the append is going to be proportional to the length of this. So the total time complexity of this is you have to worry about the lengths of all the sublists, okay? Whereas if you can rewrite this using difference lists, and then you don't need append. So difference list kind of makes append disappear, okay? So that's something. So let me show you now the difference list version, and then I'll run some code. Okay? We replace the list by a difference list. So flatten here is a function that returns a list, okay? But to make it really clear, I'm going to turn it into a procedure, and the two arguments, s and e, I'm going to make them arguments. So you see them right here, okay? S and e. So this is the output, xs is the input, and se is a difference list, which is the output, okay? And now I rewrite the three cases. So if xs is nil, then I have an empty list. Well, an empty difference list is just when s is equal to e. A difference list that's empty is a list that looks like this. SS, for example. The difference is empty. Which means an empty difference list is just s equal e. Okay? And let me do now the final one here. X, xr. I want to add the element x. And so I'm adding an element to the front of a difference list. So I'm doing like here. So s which is the front, I do equal x bar m, m for middle or something, and then I do the recursive call of me. So the x is added to the front, and then the rest is done here, okay? But the interesting one is the one in the middle here, okay? What if x and xr are both lists? Is list x is true? Then I have to do two recursive calls. Deflatten of x and deflatten of xr. And I have to append those two difference lists together. Well, what that means is that the second argument of the first one has to be bound to the first argument of the second one. These two have to be bound together. So I can write that here in the code by just doing, this is a difference list Sm, and this one starts with M. So I have the same M here. The end of the first one has to be the beginning of the second one. Okay? Sm, and then I have Me. And so the final result is Se. Okay? Se is the append of Sm and Me. Okay? So that's it. So this version of flatten is actually not doing any append at all. And otherwise it's doing exactly the same as the previous one. Okay? So I have to show you some running code. I cannot show you this kind of stuff without writing code, okay? So let me start with those are in the Docker here. Okay, so this is my Docker version of Mozart 1.4, which is taking a minute or two to start. I'm not sure why it doesn't start so easily. It worked this morning. Give it a few seconds. Okay. It's not creating the window. Check it out during the break. So I'm sorry about that. See, this is Big Sur, which is an older, this is an old Mac. It's running Big Sur, and there's a bug in Big Sur. It actually says it's actually version 11.7, but the system operation tells you it's 11.6, so that's a bug. They didn't update that. And that means the Mozart will not start, the usual Mozart, because it checks the version. Okay. Okay, so I'm sorry about that, but I will show you things on the board, okay? So I will put code on the Moodle so you can actually run the code here, huh? Okay, so let me go on. Sorry about the Mozart, I'll try to fix it during the break. So this is difference lists then, which is a very clever representation of lists that lets you do constant time append in declarative language, but only once. You can do it, but only once. Okay. Okay. Now let's go to the queues. Now let's go to the queues and the different queue algorithms we're going to show today. So let me make some room on the board. So a queue, let me remind you what is a queue. Queue is a very simple abstraction, okay? It's a sequence of elements where you can insert and delete. And the insert is happening on one side, and the delete, the elements come out on the other side. That's it. So here I insert 1, 2, 3, 4 up to 8. And when I delete elements, it's the 1 that comes out first. Okay, 1, 2, 3, 4, 8. So you can also call this a first in, first out sequence. The 1 goes in first, and it also comes out first. So that's a queue, and we're going to be showing you implementations of that. Okay. So here's a naive queue. Very simple, naive one. And it's actually not a true abstraction since I'm not protecting the representation, but I want to show you the simplest possible queue. And the question is, what is the complexity? So in order to do it, I need a helper function called but_last, which basically takes the last element out of a list. And it returns the list without the last element. So if I do but_last 1, 2, 3, x, that will return 1, 2, and it will bind x to 3. Okay, so the list will be, the x is going to be the last element. Okay, that's a helper function that I'm going to use. And now my queue is very simple. So here's my queue. A new queue, I'm going to implement 3 operations. New queue, insert, and delete. Okay. New queue returns an empty queue. So that's nil, it's just a list. Insert will insert x into a queue. So that returns the queue x bar q. I just add x to the front. Okay? And delete will remove an element from the queue, but it has to remove the last element. I'm inserting in the front, and I have to remove at the end. So delete is implemented using but_last. Okay? So this implementation here is correct. If I insert, for example, 1, 2, 3, then I delete here, I will get 1 out, okay, and so on. So I can use this to do a queue, right? It's nice, okay. But what is the complexity of this guy? Okay, what is it? What do you think? The insert and the delete. So the complexity of this, well, the insert is constant time, but the delete is doing this but_last function, so it depends on the size of the queue. So if the queue has n elements, it's going to be n, okay? So if I do n insert, or let's say I do 3 insert here, or n, let's say n, and now I do delete, and I keep doing deletes, each one of these will be order n. This will be n minus 1. If I do another one, n minus 2. So if I do a bunch of deletes here, they will be order n. Okay? So this is not so nice. That what I really want, so this is not even amortized very good. So what would be the amortized complexity here? It's still n. I have, because all these deletes together is proportional to n squared. So if I have n deletes here and n inserts, 2n operations, n squared divided by 2n, it's still proportional to n. Okay? So even the amortized complexity is bad here. So this is kind of a very slow algorithm. Okay? Okay, so this is very slow, but we want to do better. So I'm going to show you better algorithms. And the first one I'm going to show you is how to make this guy amortized constant time. Notice that this guy is amortized order n, okay? But I want to make it so it becomes amortized 1. And still functional. It'll be purely functional, okay? So now I'm going to show you the first clever algorithm, which is amortized constant time ephemeral queue. Okay? And the way to do it is you represent the queue not as a list, but you represent it as two lists. Okay? So since my poor Mozart is not running on Big Sur, I'm going to show you the examples on the board. Okay? So we represent the queue as two lists, F and R. The idea is actually very simple. F is the front and R is the back. So if we have a queue here with some elements here, the front of the queue, okay, and so the front, the inserts are coming here, okay, and the deletes are coming out here. And here we have reverse R. So when we insert, we put it on R. You see how we're doing that here? So when I'm inserting, I'm adding it to R, F-E-X-R. And when I'm deleting, I'm removing it from F. So the inserts will come here, putting it on R, and the deletes come here, will come out of F. So for example, if I start with an empty queue, here, if I do insert A into the queue, then I will do F and nil, A, nil. And now if I do another insert, I do Q, nil, B. This is B, A, nil. Okay? So I'm adding, notice I'm like adding them in the reverse order, huh? And now I want to do delete. So what happens? Well, I want to delete the elements. Well, the delete is coming here, so I need a special operation that moves the back of the queue to the front. So I need to move BA nil to here to do a delete. Okay? So let me write here. So if I have Q nil, BA nil, like before, I want to do delete. Well, the way it is first I move this. I have a special operation, and it's called check here. We'll change this to A, B nil, nil. So basically it moves this one, but it reverses it to here. Okay? And now I can do a delete. Now I do A, B nil, nil, and I delete X, and X will be equal to A. See how it works? If I do another insert now, then it will be B nil, C nil. But it also, again, I can move that to that by putting it in the front. Okay? So, but I only do it when this one is empty. So when it's empty, when I do a delete again, I will get Q nil, C nil. And now I can do check to bring the C in the front. Like that. So you see how it's working? The inserts are always going to the end, and the deletes are always coming to the front. And sometimes I have to move the back to the front. So the back to the front using the check operation. So the way it works, so let me show you now the code here. So I do an insert. FR becomes FX bar R, but I run check. And check will do the following. If the F is nil, that means if this is empty, if I've exhausted the deletes, I can't do any more deletes, then I move the R's over. I change this to reverse R nil. So the check is not done all the time. I mean, it doesn't all the time have to do the reverse. It only does it when this guy is empty. Okay? So it doesn't have to do it so much. But when it does it, it's expensive. When you do the check, you have to reverse here, which is proportional to the length of r, okay? And the delete here, notice that what the delete, how it works, is you basically remove x from the f, and then it has f1. So basically, the check will guarantee that the r is always empty, that if the f is empty, that you move the r into there, so that when you do a delete, you will not have a problem, okay? So now, what is the complexity of this guy, okay? So if I do an insert, I do an insert, I do an insert, n inserts. Those are all constant time. Okay? And now I do a delete. This delete is going to do the reverse. Okay? So this one will be n. All the inserts are 1, let's say, okay? N. But then the next delete will be only 1, because I've reversed the whole thing. Okay? So the whole complexity is n for these two n operations. So the amortized is order 1. Do you see that? In the naive one, each delete had to run but last, which is a pain. They're all slow. But here it's only one check that has to be done, only one reverse, and then all the others can be fast. You see that? How that works? So this guy is amortized constant time. And it works because of the two lists, F and R. You have two lists. That makes it a lot smarter, okay? That lets you do smarter things, whereas in the original naive one, you have only one list, which is too simple. It's not enough. You have to have a richer representation, okay? So this is neat, right? This is a nice trick, huh? This guy gives you amortized constant time, and it's just a functional program, okay? So you can run this, and it's exactly running it like before. The interface is exactly the same, okay? Okay? Now, a question for you. This guy is amortized constant time ephemeral, okay? Because if I use it in an ephemeral way, that means there's only one version. Then it will be amortized constant time. But the old queues, the old ones, are still there, of course. They don't go away. Huh? So I can use this as a persistent. I could actually use this code in a persistent way. That means I can create multiple versions, and it will be correct. Okay, let me show you what happens when we do that. So this one, I can use it persistently. So for example, I start with Q1, I do an insert, I get Q2. But I can use Q1 again and do another insert and get Q3. Now I have two versions. And I can keep going like that. Huh? I can even make more versions. And it works. It's correct. But it's not amortized constant time anymore. Okay? It's no longer amortized constant time. The amortized constant time only works when you use one version, actually. If you use more than one version, this guy will be no longer amortized constant time. Why not? So you can show that, huh? Why not? What happens if you try to do that? What happens if you try to use this one in a persistent way, which means you create multiple versions, and it works, it's correct, because these old Qs, they're just data structures, they're still there, so it actually works. But it's not amortized constant time anymore. It's correct. So this is not a solution to amortized constant time persistent. It's not a solution to that because it's not constant time anymore. Why not? Well, let's say here's an example. So here I have my Q. I do an insert. I do inserts. I do n inserts. Okay. So those are all constant time, which is what I do here. And now I do deletes. And the deletes, only the first one is going to be expensive. You only do the reverse ones, huh? Now, what happens if I use it persistently? Let's say I do a delete here, and I do another delete, starting from this one. Well, this delete will be order n, 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 n. So I get all the deletes are again expensive. So this is I'm using it persistently. And the problem is that all of these deletes are going to be slow, and therefore it doesn't work when you use it persistently. Okay? I mean, it works, but it's not amortized constant time. It's just as bad as the first one is. Okay? It's just as bad. Okay? So this algorithm is only amortized constant time ephemeral. Okay? Okay, so that's nice. This is a nice trick, huh? But maybe I can do better. What I really want is a worst case constant time ephemeral. I don't want to pay n at all. How do I do that? Okay, well, we'll make a break. After the break, I'll show you how to make it worst case constant time. Okay? Now, actually, now I got Mozart working. The problem was that Docker needs an internet. It's an active internet, so it probably has to do something. So now it works. So I'm going to show you now a worst case constant time ephemeral Q. And actually, we kind of know how to do that. The previous example here was amortized, and this was running in pure functional programming. Okay, no unbound variables here. And that's the best you can do, actually, in pure functional programming. It's not, you can't do better than that. In order to do better, you need a more powerful declarative paradigm. And if you add single assignment, unbound variables, then you can do it. In fact, we're going to use the difference list technique now that we saw before to implement the Q. We're going to represent the Q again as two arguments, just like before, but now instead of front and back, this is going to be a difference list, okay, containing the constant, the content. So in this one, both insert and delete are always going to be constant time, both of them. So here's the code. So the new Q is just an empty difference list, which is two variables that there's a same. Huh? I have Q, let me make some example here, QXX. So that's an empty difference list. That's an empty Q. And insert and delete are going to add an element to the front and remove an element from the back, actually. So it's going to be, or actually it's the opposite. The insert is adding in the back, and delete is going to be removing from the front. Okay? So here I have SE. When I insert, I'm going to bind E to XE1. So if I do an insert now, insert A, then the Q is going to be represented by a new difference list, SE1. Okay? So I'm going to bind E, so E is X here. I'm going to bind X to A, X1, let's say. And I'm going to have E1. This is going to be X, X1. But X is actually AX, X1. It's this. So this gives me AX1, X1. Okay? If I do another insert, insert B, again I'm going to bind the second one, the end. The end, I'm going to bind it here to the element followed by a new end. So I'm going to bind X1 to B, X2. So it's A, X1, X2. But A, X1 is actually A, B, X2, because of this. So this is A, B, X. So you see, I'm actually creating new difference lists each time I do insert. And if I do a delete, I will remove the first element. Now let me call this one delete Y. It's going to take S here and remove the first element, and S1 will be the new difference list. Okay? So here what it's going to do is it going to bind S. So this is S, It's going to bind A, B, X2 to Y and the new S. So Y is going to be equal to A, and S1 is going to be equal to this. Okay? And that gives me Q of S1. So S1 is BX2, and X2 is not changing. Okay? So Y is equal to A. So I've removed the first element, A, and the new difference list is BX2, X2. So that's kind of neat, right? That's kind of interesting. I mean, you're just building difference lists and managing the difference lists by adding elements and removing elements, by doing bindings. And every of these operations is constant time. And it's okay, because it's ephemeral. Okay, this will not work here. This will really not work persistently, because you're binding the things. X here, I'm binding X. You can only do that once. So this guy will not even work if you try to use it persistently. But ephemeral, it works fine, and it's worst case, constant time. All these operations are constant time. And it's purely declarative. That's pretty nice. That's exactly like the same efficiency if you write it in Java. For example, you update variables, okay? You get also the same, okay? Okay, let me show you now one small extension. This difference, the problem, there's actually a small problem here. What if I want to know, is it empty? I have to somehow compare. Is it empty? Well, that's not, you can't really do that with unbound variables. You can't really check that it's empty. Because how do you check that? If you try to test the variable, it's just going to block and wait, okay? So if you want to know how many elements are in the queue, you have to add another argument. Okay? The difference list will not tell you how many elements there are. Because of the unbound variables, you can't really count it, because you can't check whether the variable is unbound. That's not declarative. I can't test that. So I can't really check how many elements there are. So if I want to do that, I have to add an extra argument to the queue. Okay? So the previous definition does not let us know when the queue is empty. Maybe we want to test when it's empty. To know the number of elements, we have to add the size, a number, to the representation. So we will represent it as a triple then. N, which is the number of elements, and SE, which is a difference list, like before. And then it's very easy to test if it's empty. You just do q.1, is it equal to 0? Is n equal to 0? So this one will always be a number, an integer. So then our q looks like this. The new q will be 0xx. The insert will do like before, except the n will become n plus 1. And the delete, the n will become n minus 1. Okay. This one, I want to show you the execution of this. Okay. Okay. So normally the Mozart is going to work now because of the internet connection. Well, maybe like this. There we go. That's Mozart 1.4. Oops. Oh, the other one also started. Sorry, it's just slow. Okay, because Docker images are huge things. I'm not really used to that. They're very slow to start because they're several gigabytes. Okay, so here is now. I'll show you the other one. The one with the difference lists. So here's the code. Okay, so you can see the code. It's the same with the triple NSE, and I'm doing n plus 1, n minus 1, and I'm doing the difference list operation. Okay. So now if I do something like this, Q1, Q in, and I do Q is equal to insert, I create a new queue, and I do A, then I browse Q. I want to see what it looks like internally. You see here the way it looks like? It's 1 A bar underscore underscore. So those two underscores are actually the same variable. The browse doesn't know that, but they're actually the same variable. If I do another insert, QB, this, then you can see it's 2 and then A bar, B bar underscore, and underscore. Okay? Notice a funny thing. Let me make it a little bigger. Notice a funny thing. When I create the second one, Q2, the first one is changed. Notice that because I bind a variable inside the second insert, the first Q1 there is now a difference list, because I bound the argument. See, A, B bar, B bar. It's still the list A, but I've bound the second argument, so it's my difference list is kind of used up. I cannot bind it again. But the second one, so that's why it's ephemeral, and the second one now has an unbound variable here and here, so I can still go farther if I want to. Q3. So I do insert. Q2, C. That was Q3. So now I insert a third element. So the bottom one says Q3 ABC bar underscore underscore. But the two previous ones I'm binding. So they're not, I've used it up. I cannot bind anymore. But here in the third one, I still can use this difference list. I can only use the most recent one. The previous ones, I've bound the second argument. So it's used up. The differences can only be used once. Okay. Okay, so you see how it works, huh? And the 1, 2, 3 gives me the size, huh? Okay, now I'm going to show you a little bit of magic. And this is actually, we're actually going to do a little bit of logic programming. So this is kind of a shout out to logic programming. And I just want to show you that there's even more paradigms that I won't go into logic programming really in this course, but this example is actually doing logic programming. Do you know that with the cue that I just showed you, I can do the delete before the insert, which is kind of magic, huh? Usually you insert an element in a queue and then you delete it. You can't delete before you insert, but with this one you can do that. It lets you delete before the insert, and it actually works. Okay? So I delete here. For example, I'm deleting, I create a queue here, Q1. I delete, it's empty, yeah? I delete an element, X. I display that element. Well, it's unbound, but it's like a slot. And if I then do an insert, then it will fill that deleted element. So the deleted element, it's like I've borrowed. I delete an element, but I don't know what it is yet. But then when I do an insert, I know what the deleted element was. It's foo, okay? The delete kind of creates a slot that's filled in by the insert. So the deletes and the inserts are kind of commutative. Every delete corresponds to an insert, but the delete can be done before or after. It doesn't really matter. That's very funny, yeah? So let me show you that, and then I'll explain how it works. I'll explain to you the magic of that. Okay. So let me create another empty cube. Create a few ones here. So this is an empty cube. Show it to you. 0, and the two variables are actually the same. And now I will do delete. Okay. I will do Q2 is equal to delete, but I need an X. I still don't know what the result is, so declare X in delete Q1 X. So what is going on here? I can delete, there's nothing in the queue, it's empty, and I will delete an element. But the delete is actually binding variables, so it's just going to work. Look what it says. The queue now has -1 element, but there's no element here. But the element is sticking at the end. It's like a reserved slot, in a sense. Okay? And if now I insert an element, if I do insert Q2 foo, then it will fill the slot. Okay? Let me first browse X here. So X is the element I've deleted. X is the element of that I've deleted. But if I insert foo, then X will be equal to foo. And now the queue again has 0 elements. So if I browse the Q3, it has 0 elements. So this Q is actually more powerful than the other one. Here, I can actually have negative numbers of elements. That's weird, huh? Usually you put elements in a queue and you would take them out. But here, if I take them out, I'm actually reserving slots. And when I put the elements in, they will use the slots that I reserved, in a sense. Okay? So what's really going on here? Let me explain a little bit more on this, because this is actually leading to a new programming paradigm called logic programming. So the question, how can this work? How can you do a delete before an insert? Okay, let me explain first, and then I show you more concretely. The reason why this Q has a special power, it's because of logical equivalence. When we defined declarative programming, we said two stores are equivalent if the two logical formulas are actually saying the same thing in a sense. Huh? And this is why the Q can have a negative number of elements. But that's the real reason. But I will show you in a second what's really happening with the bindings. The Q definition guarantees that the deleted elements are equal to inserted. It's because the binding can be done in any order. Binding is symmetric. You don't have to bind elements before unbound variables. If you do it in the opposite direction, it works. The operation is actually more general than just binding a variable. It's called unification, this operation, and it's actually making two things equal. Okay? We can delete an unknown variable and insert a value later. In fact, we're doing more than just functional programming. We're doing logic programming here. So the Prolog language, which is logic programming, will let you do things like this. Okay, so that's all words, but let me show you really what happens in terms of the bindings. Okay, so let's start with an empty Q here. SS. I make one of them red, the left one I'll just color it red, and the other one green, to show you the two different bindings. So let's say I delete X. Okay? So when I delete X, I'm actually removing an element from the front. Let's remove it. What does that mean? Sorry, I made these slides yesterday, so let me make it nicer. Okay, this is more clear. Delete Y, actually, yeah? This is just-in-time slide creation. So I delete. Well, the delete operation will bind the beginning of the difference list. It does S equal Y is 1. Okay? And the insert operation will add S X to the end. So it does S equal X bar E1. So if the Q is empty, I'm actually doing two bindings of S. Okay? Two bindings of S. S equal Y is 1 and S equal X E1. So what happens? I'm doing two bindings of S here. But for logic programming, that's okay. Each binding is a logic formula that goes into the store. So S equal Y is 1 is this, and this is logic formula in the store. And the other one is also logic formula. So the store just has both logic formulas. It's pure logic. It has that. So what does this mean? Well, we can simplify this. If S is equal to Y is 1 and S is equal to X E1, then Y has to be equal to X and S1 has to be equal to E1. That means the deleted element, Y, is the same as the inserted element. It can be done in both directions. This is actually logic programming. It works because the store is actually representing a formula in logic, and whenever I do a binding, I'm adding information into the store, logic information, and the store is actually representing that information logically. It's logic programming, okay? So I don't want in this course, to be clear, I'm not going to show you really logic programming in this course, but this example is giving you a little bit, to show you a little bit of the power of logic programming. We're actually manipulating logic formulas, okay? So I'm actually making a kind of shout out to Prolog, which is a logic programming language. In this example, the Q is actually doing logic programming. Both insert and delete are done with the binding, but because of logical equivalence, the bindings are imposing logical equality. So first order logic, yeah? This is logic programming, and logic programming is another declarative program paradigm, where instead of doing functions, you manipulate logic formulas, okay? It's more general than functional programming, actually. Data structures can have unbound variables in them, and binding is bidirectional. So this is, in fact, a new declarative paradigm, and a very powerful one. This one was first really made, worked really in the Prolog language. Prolog is an acronym, it means programming in logic. So we're not going to see Prolog in this course, but I think that my colleague Kim Metz sees Prolog in his paradigms course. Also, constraint programming is actually a generalized version of Prolog. So constraint programming is a kind of logic programming, and we have the very good luck to have experts in constraint programming in the department, Yves Deville and Pierre Schoos. They actually, there are courses on constraint programming. So if you want to go really, see, this is only showing you a small piece of the power. It's an extremely powerful declarative paradigm. It's actually more powerful than standard functional programming. But it's not part of this course, okay? Maybe it should be one someday, but it deserves a whole course by itself. Okay? So this is just a kind of shout out. This amortized, constant time, ephemeral Q is actually just an example of what you can do with logic programming. Because the bindings are symmetric, the insert and the delete can be done in any order, and it still works. Okay? And you can see how it works by following what's going on in the store. It's because it's a logic formula. Okay, so that's all. That was just a quick shout out to logic programming. Okay, but I'm not going to present more on logic programming in this course. But if you're curious, it is really interesting. Prolog is a language now that is 50 years old. In fact, this year is the 50th anniversary of Prolog, because it was invented in 1972. So there's kind of a celebration going on now in the Prolog community because of the 50th anniversary. But Prolog is an old language, but constraint programming is a very recent research topic. It's generalized to very powerful kinds of logic inference. Okay? So I really recommend the course on constraint programming for you, and also the course on programming paradigms if you want to learn Prolog. Okay, so let's go on now. Now we've done as far as we can with ephemerals. Now I want to make things persistent, okay? Now, again, I'm going to show the power of lazy evaluation. Okay? So persistence is the thing now. Okay? Persistence is a strong property. It means whenever you create and do an operation, the old version is still existing and you can still use it and it's still efficient. Okay? Many versions can exist simultaneously. So this is actually hard to do. in any paradigm. This is hard, okay? All stateful programming with variables that you can update, Java and Python, it's all ephemeral. Whenever you assign a variable, the old value, poof, is gone, okay? All algorithms using mutable state are ephemeral. So all the algorithms you saw in your algorithms course are ephemeral, okay? They're not persistent. You can't really have multiple versions. The only way is to make explicit copies, like you make a copy of the data structure. Then you have to manage those copies, and it gets complicated. But today I'm going to show you how to do persistence by using lazy evaluation. In fact, by using lazy evaluation, you can make efficient, persistent algorithms. It's another amazing property of laziness. Okay, so let me show you one example. The first example will be an amortized constant time persistent queue. And then we'll go into the biggie, which is worst case constant time persistent queue, which is, it works, but it's a little bit more complicated. The amortized one is a little bit easier. Okay. So let me show you. Well, first we need a helper function, a lazy append. So this is the same as for quicksort, okay? We need a lazy append function. So this is just the append made lazy. And what it does is, if you ask for elements, each time you ask for an element, the case statement will ask for elements from its first argument, okay? So whenever I ask for an element, here I do L_append, for example. If I do L.1, I'm asking for the first element. That will activate the lazy suspension, and the case statement will ask for the first element of XS. Okay. So this is a lazy append. So this is our helper. We're going to need this. Okay. So what's the idea? Again, we're going to implement our queue, and we're going to choose another representation, yet another one. Okay. Remember, we had already several representations, huh? Now we're going to choose yet another one. So remember, we had several representations. We had the list, we had the front and the back lists, front and reverse. We had difference list. And now we're going to have another representation that we designed carefully. We're going to have a tuple of 4 elements. And actually, it's inspired by F and R. We're going to have the length of F, the length of R. And we need to know the lengths. So we're going to add 2 elements which tell us the length of F and R. Okay, just integers, natural numbers. And the idea, again, is to move elements from R to F. So it's very similar to the amortized one we did in functional. Okay? But this move will now be done with the lazy suspension. It's not going to be done by calling the function immediately. It's going to be done lazily. Okay? Okay. So that's the idea. And now, how do we make this whole beast amortized constant time? That's the trick. That's the subtlety. Okay? So how do we make it amortized constant time? Well, it has to do a reverse. Okay? So basically, it has to reverse R and append F to it. It has to do a reverse. Okay? It has to do a reverse. But reverse cannot be made incremental. There's a problem with reverse, which I'll explain in a few minutes. Reverse is kind of a nasty function. You can't really make it incremental. Because if I reverse a list, if I do reverse, so the idea is very simple. If I do reverse 1, 2, 3, then the result will be 3, 2, 1. But if I want the first element of this, the first element is 3. But 3 is at the end of the list here. That means in order to get the 3, I have to go all the way to the end. Basically, I have to do all the work. I can't make it incremental. There's no way to make the reverse incremental, okay? So how do we make our thing amortized? So the trick is we still want an amortized. So we have this expensive operation, reverse, okay? And the way to make it amortized is to make sure we don't do the reverse very often, okay? We want to do it as little as possible and at the right place so that on average we have constant time, okay? So what we will do is we will do the lazy suspension, we will create it in advance. We will not do it like before, where we do reverse when we need to make the elements. We will do it in advance. Okay? And we will, to make it amortized, we will use a technique called the banker's method. When you do an expensive operation, you have to pay money. The time, it's like money you're paying. And the banker's method to make an amortized algorithm is to save money in the bank. And when you have enough money in the bank, then you can buy the house, okay? So each time I do a cheap operation, I'm saving €1. And when I have n euros in the bank, I can do the reverse, which takes n euros, okay? So basically, I'm doing something where I'm saving money in the bank, n, and here I can do my n my order n expensive operation. So that's kind of a general technique. It's called the banker's method because that's how you save money in the bank, okay? We do n cheap operations, and then we can do the expensive operation. So we kind of will do like that. And it's a little bit tricky. So let me show you the code, and then I'll show you how it works. So here's the code. It's actually quite similar to the code of the regular amortized functional one. So let me go through it. So here I have insert and delete. And if you look at F and R, so start by looking at F and R. F and R. Again, I do F and I put X bar R in the end. And the length of R increases by 1. That's reasonable, huh? I'm just doing that. And the delete will remove the element from F, and it will decrease the length of F by 1. Okay? So it's just like before, actually. The difference is in the check. Okay, so we have this check now. It looks at the tuple, and it will create a lazy suspension. Here it is. Okay. Notice that I'm doing append of F and reverse R. So it's basically doing append of F and reverse R. Okay. That's what it's doing. And that is moving, that's the new F. And the new R will be nil. Okay. So, but I'm doing it lazily. So I have a lazy append of F with reverse R, I put it in a lazy. I make it lazy. But the reverse is not lazy, huh? It means that doing the reverse will be lazy. Once I do it, I do the whole thing. But I can delay doing the reverse. Okay, so the reverse is in a lazy suspension. So this red one is moving it in. And the length of F will be ln F plus ln R. And the length of R will be 0. The new R will be 0. So I'm moving all the elements from R to F. But I'm doing it lazily. And the whole trick of this approach is this condition here. When do I do this? When do I create the lazy suspension? Well, I do it when the length of f is less than the length of r. That's a weird condition, so the trick is you want to understand the condition, okay? Okay, so I'll show you a kind of example to show you how it works. So the trick is, so this lazy suspension is going to do the work, okay? So you see that it works, huh? The trick is, when do you do it? You have to do it in a smart time. You have to do it so that it's amortized and so that it makes it persistent, which means that if you have multiple versions, that you only pay once for the operation, okay? So let me show you first the idea, and then I'll show you how this one is doing it, okay? The trick is to make sure that the algorithm that it creates when it creates the lazy suspension, okay? So assume we are inserting elements, okay? If we insert elements, the R gets bigger. And eventually the R gets bigger than F, and then this condition is true, and we create lazy suspension, okay? And that makes the new R empty. So it empties out the R, and the F gets bigger. And if we keep inserting elements, the R gets bigger again, until it gets bigger than F, and then again we move elements over. So whenever we insert a bunch of elements, when we insert enough of them, we will move over, okay? So that's kind of vague, but I'll have to show you with an example, okay? But let me first show you the idea by comparing two algorithms. So here I will show you the ephemeral one, and here I will show you the persistent one. So the ephemeral one we saw it already. Let's say we do inserts. 1, 1, 1, 1, 1. We do inserts, okay? And now we do delete. The delete takes n, okay? And we do inserts again. It will be 1, okay? 1. So you see, if we do n inserts, this delete will do n. But that's okay if there's only one version, right? Because the total here will be, you have n operations with 2n times, so it's still amortized. But you can't use this in a persistent way. If you try to use it in a persistent way, it goes like this. We have n. But if starting from this version, I do another delete, I'm allowed to do that. It will also be n. If I do n deletes, they're all n. So that if I try to use it persistent, it won't work. See that? Doesn't work. Because every single delete here is going to take n. As long as I'm only doing one version, then it's okay. Because I'm spreading this n over all these. But if I do many versions starting here, the same place, then each one of them will take n. That's a pain. Well, laziness is going to save us now. Laziness will save us. Because how does this work in a lazy scheme? So again, I do a delete. But the lazy suspension is created here. Let's say, before I do the delete. So this, when I do a delete here, it's going to activate the lazy suspension. And this one will do a computation, will bind variable here. Okay? So this will take n. This lazy suspension created in advance will be activated here. But what happens if I do a second delete? Well, the lazy suspension is already executed. So the delete will just use the result. So the other deletes will be constant time.
So I don't have this problem where I will do the delete every single time. Here I'm only doing this execution once. And the reason is that I create the lazy suspension in advance, and the result of this lazy suspension is seen by all of these guys. So the second guy doesn't have to do it. It's already done, and so on. So laziness lets you put the computation early so that when you do it, all the people afterwards will see it, okay? So that's how it works, okay? Okay, now, we're almost done today, so I'm not going to, this condition, this nice condition here, len f less than len r, I'm not going to explain it today. I will explain it next week. I think it's good to do in 2 steps so that you can understand it. But I will say one more thing today, okay? You see the idea, so it's important to understand these diagrams, huh? It's important to understand why the ephemeral algorithm works amortized ephemeral, but not persistent. And it's important to understand why laziness will let it work persistently. And then the only trick is to figure out exactly where to put this lazy suspension so that it works. Okay? So that you don't want to do it too early or too late. You have to pay for this thing to make it amortized. Okay? But you see the idea. The lazy suspension is sitting there early on. And because it's early, the delete done later, everybody done later will see the result of this. Not just this delete, but this one too. Whereas here, when I do a delete, I'm doing the operation right here. This second guy will not see the result, what I'm doing here. Huh? And the third guy will not see it either. Each guy has to do it separately. Okay? So laziness lets you put the computation earlier so that everybody can see it. Okay? And that's why it can make things persistent. Okay, maybe I stop here because probably your brains are probably full, and I will refresh your memory, and the next time I will explain it again. I probably should be much easier to understand. Okay, so let me stop here, and then next time I will show also again the magic why it's persistent.